More than 70% of the surface of this planet is covered by ocean. That is not a metaphor or an exaggeration. It is the single most defining feature of the world we live on, and yet it is also the feature we understand the least. The average depth of the ocean is more than 12,000 feet. In some places, it drops far deeper than that, plunging into trenches so remote and so pressurized that we have sent more people into orbit around the Earth than we have sent to the bottom of the sea. As of the middle of 2024, only about 26% of the ocean floor had been mapped using modern high-resolution sonar. That means nearly 3/4 of the surface beneath the waves remains, in the most literal sense, unknown. We have better maps of Mars. We have better maps of the far side of the moon, the floor of our own planet. The ground beneath the water that surrounds every continent is still largely a blank space on the chart. Tonight, we are going to descend into that blank space. Over the next 2 hours, we will travel to the deepest trenches on Earth, where the pressure alone would crush a human body like a paper cup. We will listen to sounds recorded by military hydrophones that no scientist has ever been able to explain. We will visit structures on the ocean floor that look as though they were built by hands, not shaped by nature. We will meet creatures so vast and so alien that they defy the boundaries of biology. And we will walk through stretches of ocean where ships, planes, and submarines have vanished without explanation, leaving nothing behind. Every story you're about to hear is real, every discovery is documented, and many of them remain, even now, without a satisfactory answer. So settle in, let the lights go low, and let the ocean tell you what it has been hiding. Our first stop lies 7 miles beneath the surface of the Pacific, in a place so deep that Mount Everest could be swallowed whole and still leave more than a mile of water above its peak. In the western Pacific Ocean, east of the Philippines and roughly 200 miles southwest of the island of Guam, the Earth's crust bears a scar so deep and so vast that it took humanity more than a century just to measure it accurately. It is called the Mariana Trench, and it is the deepest place on the surface of our planet. The trench itself is enormous. It stretches in a crescent shape for more than 1,500 miles across the ocean floor, averaging about 43 miles wide. But it is not the trench's length or width that captures the imagination. It is the depth. At its lowest point, a narrow slot-shaped depression known as the Challenger Deep, the ocean floor drops to approximately 10,935 meters below sea level. That is nearly 36,000 feet, nearly 7 miles straight down. To put that in perspective, if you placed Mount Everest at the bottom of the Challenger Deep, its peak would still sit more than a mile beneath the waves. The trench was first detected in 1875, during one of the most ambitious scientific voyages ever undertaken. The British Survey, ship HMS Challenger, on a global circumnavigation that lasted more than 3 years, lowered a weighted-sounding rope into the Pacific near the Mariana Islands, and recorded a depth of roughly 26,000 feet. It was the deepest measurement anyone had ever taken of the ocean, and it stunned the scientific community. But the true depth of the trench would not be known for another 75 years. In 1951, a second British vessel, HMS Challenger II, returned to the same stretch of ocean equipped with echo sounders and taut wire measuring systems. The crew lowered 140 pounds of scrap iron on a wire into the water and waited. It took 90 minutes for the weight to reach the bottom. The reading that came back confirmed what many suspected. The Mariana Trench was far deeper than anyone had imagined. It was in fact the deepest point on the surface of the Earth. For nearly a decade after that discovery, no one attempted to go there. The pressure at the bottom of the Challenger Deep is roughly 16,000 pounds per square inch, more than 1,000 times the atmospheric pressure at sea level. At that depth, the water temperature hovers just above freezing, and the darkness is absolute. No sunlight reaches the bottom. No current stirs the sediment. It is by every measurable standard one of the most hostile environments on the planet. And yet, on January the 23rd, 1960, 2 men decided to go anyway. Jacques-C. Piccard, a Swiss oceanographer and engineer, and Lieutenant Don Walsh of the United States Navy descended into the Challenger Deep aboard the Trieste, a deep diving vessel known as a bathyscaphe. The journey took 5 hours. For most of the descent, Piccard and Walsh sat in a tiny steel sphere, barely large enough for 2 men, watching the darkness press in from every direction. At one point, as they neared the deepest part of the trench, they heard a loud, sharp crack. It was the sound of the observation window's outer plexiglass panel fracturing under the immense pressure. The 2 men looked at each other and continued the descent. When they finally reached the bottom, they stayed for just 20 minutes. The sediment kicked up by their landing was so thick that they could barely see anything at all. But Piccard reported something extraordinary. Through the swirling clouds of silt, illuminated by the vessel's single floodlight, he glimpsed what he believed to be a flatfish resting on the seafloor. If true, it would mean that vertebrate life existed at the very bottom of the world, in a place where the pressure should have dissolved calcium from bone and made skeletal structures impossible. To this day, scientists debate whether Piccard actually saw a fish, or whether it was a type of sea cucumber, a boneless creature more suited to the crushing depths. The question has never been definitively answered. It would be more than 50 years before another human being followed Piccard and Walsh to the bottom. In 2012, filmmaker James Cameron piloted a specially designed one-person submersible called the Deep Sea Challenger to a depth of roughly 35,787 feet. Cameron spent several hours on the seafloor, collecting samples and recording footage of a world that had been seen by human eyes only once before. His cameras captured a barren landscape of pale sediment, scattered with the ghostly shapes of creatures adapted to a life without light, without warmth, and without mercy. Then, in 2019, a Texas-based explorer named Victor Vescovo made the journey again, this time reaching 35,853 feet. When Vescovo looked out the viewport of his submersible, he saw something that no one expected to find at the deepest point on Earth: a plastic bag, and beside it the wrapper from a piece of candy. It was a grim reminder that humanity's reach extends even to places we cannot survive. Despite the near impossibility of the conditions, life persists in the Mariana Trench. In fact, it thrives in ways that continue to astonish researchers. The most common organisms at the very bottom are Xenophyophores, single-celled creatures so large they can reach the size of a mango. They resemble giant amoebas, engulfing food particles from the sediment in slow ancient rhythms that have likely remained unchanged for millions of years. Alongside them are amphipods, small crustaceans that look like shrimp and scavenge anything that drifts down from the upper ocean. Scientists discovered that the amphipods living in the Mariana Trench have developed a remarkable adaptation. They incorporate aluminum into their exoskeletons, making them the first known species on Earth to use that metal for structural reinforcement. The aluminum, absorbed from sediments on the seafloor, allows them to withstand pressures that would crush almost any other living thing. In 2017, researchers identified a species now known as the Mariana snailfish, a small, translucent fish with a skeleton made entirely of cartilage. Found at a depth of roughly 8,000 meters, it is the deepest living fish ever recorded. Its body is soft, almost gelatinous, designed to move with the pressure rather than resist it. When brought to the surface, it literally falls apart. A CT scan of one specimen revealed a tiny crustacean still visible inside its stomach, a snapshot of life and death at the bottom of the world. During a 2-month expedition in 2016, researchers from the National Oceanic and Atmospheric Administration captured footage of a jellyfish unlike anything previously documented. Glowing with soft bioluminescent light, it drifted through the trench like a visitor from another dimension, its tentacles trailing behind it in slow, deliberate arcs. The species has still not been formally named, and in 2024, Chinese researchers aboard the submersible Fenduje, which translates to Striver, completed 23 dives into the Mariana Trench and discovered the deepest known animal communities ever observed. Thousands of worms and mollusks, living at depth between 8,000 and 31,000 feet, clustered around features on the seafloor in patterns that suggested a complex, interconnected ecosystem far below the reach of sunlight, far below the reach of warmth, and far below the reach of almost everything we once assumed about where life could exist. But the Mariana Trench holds more than just life. It also holds evidence of our impact. A 2018 study published in the journal Geochemical Perspectives found that microplastics were disturbingly common in the deepest waters of the trench, having filtered down through miles of ocean to settle at its lowest points. Researchers also detected high levels of industrial pollutants, including PCBs, in amphipods collected from the trenches. These chemicals, banned decades ago in most of the world, had travelled through the food chain and concentrated in the bodies of creatures living at the very edge of the biosphere. As one researcher put it, the fact that such extraordinary levels of pollutants were found in one of the most remote and inaccessible habitats on Earth brought home the long-term, devastating impact that humanity is having on the planet. The Mariana Trench remains in many ways the last great unexplored frontier on Earth. Every expedition that descends into its darkness returns with something unexpected, a new species, a new geological feature, a new question that the existing science cannot answer. The pressure alone makes sustained research nearly impossible. Equipment fails. Submersibles strain under the weight of 7 miles of water, and the trench itself is so vast, so long, and so deep that mapping it in detail would take decades of continuous effort. For now, we know just enough to understand how little we know. The deepest place on Earth is also the most mysterious, and it guards its secrets well. But it is not only the things we can see in the deep that unsettle us. Sometimes it is what we hear. In the summer of 1997, a team of researchers at the National Oceanic and Atmospheric Administration's Pacific Marine Environmental Laboratory was engaged in routine work. They were monitoring the ocean for signs of underwater volcanic activity using a network of hydrophones, underwater microphones originally developed during the Cold War as part of the United States Navy's sound surveillance system. That system, known as SOSUS, had been designed for one purpose: to detect the acoustic signatures of Soviet submarines moving through the deep ocean. By the late 1990s, with the Cold War over, NOAA had repurposed portions of the network for scientific research, listening not for submarines but for the sounds of the ocean itself. Earthquakes, volcanic eruptions, the calls of whales migrating across entire ocean basins. It was painstaking, often monotonous work. Hours of silence punctuated by the occasional rumble or groan of a restless planet. And then, in the summer of that year, the hydrophones picked up something that did not fit any known category. It was an ultra-low frequency sound of extraordinary power, detected by sensors stationed more than 5,000 kilometers apart across the Pacific Ocean. The sound rose rapidly in frequency over the course of approximately 1 minute, and its amplitude was enormous, far louder than any biological sound ever recorded. The researchers gave it a name. They called it the bloop. When the recording was sped up to 16 times its normal playback speed, which is standard practice for making infrasound audible to the human ear, it produced an eerie, almost organic tone. It sounded to many who listened like the call of a living creature, a massive unknown animal somewhere in the deep Pacific, crying out across thousands of miles of open ocean. The resemblance to a biological vocalization was so striking that it immediately captured the attention of both the scientific community and the wider public. NOAA's Christopher Fox, one of the researchers who analysed the recording, stated in a 2001 interview that the sound's profile did indeed resemble that of a living creature. The rapid variation in frequency, the shape of the waveform, the way it rose and fell, All of it was consistent with the kinds of sounds made by marine animals. But there was one crucial difference. The bloop was several times louder than the loudest known animal on Earth, the blue whale. If a creature had produced it, that creature would have to be dozens of times more massive than any animal known to science. The implications were staggering. Either there was something alive in the deep ocean that dwarfed every other organism on the planet, or the sound had come from something else entirely. For years, the bloop remained unexplained. Theories multiplied. Some speculated about unknown species of colossal squid or whale lurking in the unexplored waters of the southern Pacific. Others suggested underwater military experiments or seismic events of unusual character. The sound's approximate point of origin was triangulated to a remote location in the South Pacific, roughly 50 degrees south latitude and 100 degrees west longitude, a desolate stretch of open ocean west of the southern tip of South America, with no record of unusual human or animal activity. It was the kind of place where anything could hide. Then, beginning in the mid-2000s, NOAA researchers started deploying hydrophones closer to Antarctica, and as they listened to the sounds of the polar ocean, something familiar began to emerge. Certain noises recorded near the Antarctic coast, produced when massive blocks of ice fractured or slid beneath the waves, had an acoustic signature that was nearly identical to the bloop. The rising frequency, the duration, the sheer power of the sound. It all matched. The only difference was scale. The bloop had not come from just any piece of ice. It had come from something colossal, a glacial collapse of immense proportions. In 2012, oceanographer Robert Giac and his team made it official. The bloop, they concluded, was the sound of an ice quake, a massive iceberg breaking away from an Antarctic glacier with enough force to send acoustic energy rippling across the entire Pacific Ocean. The sound had travelled thousands of miles through a natural phenomenon known as the SOFAR channel, a layer of deep water that acts as a kind of acoustic highway, carrying low-frequency sounds over vast distances with minimal loss. When played back at normal speed rather than the sped-up version that had become famous, the bloop sounded less like a creature and more like what it was: thunder from the ice. The resolution was elegant, but for many, it was also a little disappointing. The idea that something enormous and unknown was calling out from the deep had captured the imagination of millions. And while the bloop was eventually explained, the ocean has produced other sounds that remain far more elusive. The upsweep, for instance, was first detected in August of 1991, when NOAA began recording with its Pacific hydrophone array. It consists of a long series of narrow-band upsweeping sounds, each lasting several seconds, emanating from a source somewhere between New Zealand and South America. The sound appears to be seasonal, peaking in spring and autumn, but its origin has never been identified. It is still being recorded today. Then there is Julia, a strange sound captured in 1999 and attributed tentatively to a large iceberg scraping along the ocean floor, and the Sea Train, recorded in March of 1997, a sound that rises to a steady frequency and is believed to come from a grounded iceberg near Cape Adare in the Ross Sea. And perhaps the strangest of all, the ping, reported in the 2016 by hunters in the Fury and Hecla Strait in the Canadian Arctic. They described a pulsing rhythmic sound emanating from the seafloor that was so persistent it appeared to be driving animals away from the area. Canadian military investigators were dispatched to the region, but no definitive source was ever found. The ocean is not silent. It is full of sound, full of voices, full of signals that we are only beginning to learn how to interpret. Some of those signals come from volcanoes and earthquakes, from the slow grinding of tectonic plates against each other in the dark. Some come from marine life, the songs of whales, the clicks of dolphins, the strange percussion of snapping shrimp. And some come from places and sources that we have not yet identified, frequencies that ripple through thousands of miles of seawater and arrive at our instruments as questions we cannot answer. The ocean's voice is vast and strange, but stranger still are the shapes it hides on its floor. In June of 2011, a team of Swedish divers were searching the floor of the Baltic Sea for something far more mundane than a mystery. Peter Lindberg and Dennis Asberg, co-founders of a small exploration outfit called the Ocean X Team, were treasure hunters. They made their living scanning the cold, murky waters of the Baltic for old shipwrecks, hoping to find cargo that could be salvaged and sold. The Baltic Sea is rich with such wrecks, its low salinity and frigid temperatures preserving wooden hulls for centuries. On a good day, a team might locate a merchant vessel from the 1700s or a wartime freighter with its hold still intact. On most days they found nothing at all, but on this particular sweep, roughly 60 kilometres offshore between Sweden and Finland, their side-scan sonar returned an image that stopped the entire crew cold. On the screen, at a depth of approximately 90 metres, sat a massive, roughly circular object on the seafloor. It measured about 60 metres across, and its outline was eerily symmetrical. Even on the grainy sonar display the shape looked deliberate. It did not resemble a rock formation or a shipwreck. It looked, to the untrained eye, almost like a disk, and behind it, stretching for roughly 300 metres across the seabed, was a long flattened impression that some interpreted as a runway, as though whatever the object was had skidded across the ocean floor before coming to rest. Lindberg and Asberg knew immediately that they had found something unusual, but it would be another year before they returned with better equipment to investigate. When the Ocean X team came back in 2012 to dive the site, they reported something even more puzzling. According to the team, their electronic equipment began malfunctioning as they approached the object. Cameras, sonar instruments, and even their satellite phone stopped working when they were directly above the formation. Once they moved roughly 200 metres away, everything came back online. Whether this was a genuine electromagnetic phenomenon or a convenient narrative to heighten public interest has been debated ever since. The sonar image was released to the press, and the reaction was immediate and enormous. Journalists noted that the circular shape bore a striking resemblance to the Millennium Falcon from the Star Wars films. Within days, the story had gone global. Theories poured in from every corner of the internet. A sunken UFO, a Nazi submarine base from the Second World War, a fragment of the lost city of Atlantis, the portal to another dimension. Scientists, however, were less enthusiastic. Volker Bruckert, an associate professor of geology at Stockholm University, examined rock samples that the Ocean X team had brought up from the site. His findings were straightforward. The samples were granites, gneisses, and sandstones, rock types entirely consistent with the glacially shaped geology of the northern Baltic Sea. Among the samples was a single piece of basaltic rock, which is volcanic in origin, and therefore somewhat unusual for the Baltic floor. But Bruckert explained that glaciers could easily have transported such a rock from elsewhere during the last ice age, which ended roughly 12,000 years ago. The entire northern Baltic region, he noted, has been heavily influenced by glacial thawing processes, and both the formation and the rock samples were likely shaped by those natural forces. Finnish planetary geomorphologist Jarmo Korteniemi went further. He examined regional bathymetric data and identified the so-called runway behind the object as part of a larger group of similar mounds, oriented in the same direction, across the seabed. These formations, he explained, are drumlins, elongated hills of sediment deposited and shaped by moving glaciers. They are common in formerly glaciated regions and bear no relationship to crash landings or artificial construction. Dan Fornari, a marine geologist at the Woods Hole Oceanographic Institution in Massachusetts, weighed in on the sonar image itself. He cautioned that the resolution of the scan was far too low to support any detailed interpretation. The sonar used by the Ocean X team was a commercial-grade side-scan unit, not the high-resolution multi-beam systems used in serious marine research. Fornari noted that the image contained numerous artifacts and distortions that made it unreliable for drawing conclusions. Despite these assessments, the Baltic Sea anomaly, as it came to be known, refused to fade from public attention. The Ocean X team continued to promote the discovery, appearing in documentaries and interviews, and at one point announcing plans to take wealthy tourists to the site by submarine. Jonathan Hill of the Mars Spaceflight Facility, observing the spectacle from the sidelines, offered a pointed comment. "Whenever people make extraordinary claims," he said, "it is always a good idea to consider whether they are personally benefiting from the claim, or if it is a truly objective observation. The only original image that exists of the anomaly is the low-resolution sonar scan captured during its discovery. Every detailed rendering that is circulated online, every computer-generated model that appears to show intricate stairways and smooth metallic surfaces, is an artist's interpretation. The object itself, whatever it may be, has never been photographed in high resolution. It remains at its core a blurry shape on a screen, a glacial deposit most likely, an artifact of poor sonar resolution, almost certainly. And yet, the story endures, because the deep does not have to be alien to be mysterious. Sometimes it only has to be unknown. From glacial deposits mistaken for spacecraft to structures that genuinely blur the line between nature and architecture, the ocean floor continues to defy easy explanation. Off the southernmost coast of Japan, where warm Pacific currents sweep past the remote Ryukyu Islands, divers found something in the 1980s that has divided the scientific community for nearly 4 decades. And unlike the Baltic anomaly, this one is not a matter of sonar resolution. You can swim right up to it. You can touch it. And when you do, you are left with more questions than you had before. Yonaguni is a small island at the far western edge of Japan, closer to Taiwan than to Tokyo, surrounded by deep water and strong currents. For years it was known primarily among divers for one thing, the large schools of hammerhead sharks that migrate through its waters each winter. But in 1986, a local diver and tourism operator named Kihachiro Aratake was scouting for new dive sites along the island's southern coast when he came across something that took his breath away. Resting on the seabed, roughly 100 meters offshore, and between 10 and 25 meters below the surface, was a massive rock formation that looked, for all the world, like a stepped pyramid. The structure, which came to be known as the Yonaguni Monument, is enormous. It measures more than 165 feet long and roughly 65 feet wide, and it rises about 25 meters from the seafloor. Its surfaces appear to feature sharp angular edges, flat terraces, what look like stairways leading from one level to the next, right angles that seem too clean, too precise, to have been carved by water alone. When photographs of the formation began circulating among archaeologists and geologists, the debate was immediate and fierce. On one side stood Masaki Kimura, a marine geologist at the University of the Ryukyus. Kimura spent years studying the site and concluded that the formations were man-made, the remains of a stepped monolith built by an ancient civilization. He initially estimated that the structure was at least 10,000 years old, dating it to a period at the end of the last ice age when sea levels were significantly lower and the formation would have been above water. In a report presented to the Pacific Science Congress in 2007, he revised his estimate downward to 2,000 or 3,000 years ago, suggesting that tectonic activity had submerged the structure after it was built. Kimura claimed to have identified not just a pyramid, but also castles, roads, monuments, and even a stadium within the underwater complex. To him, the Yonaguni Monument was nothing less than the remains of a lost civilization. On the other side stood Robert Schoch, a geologist from Boston University, who made multiple dives to the site and collected rock samples for analysis. Schoch acknowledged that the monument looks, at first glance, strikingly artificial. The sharp angles, the flat surfaces, the apparent stairways, all of it suggests the hand of a builder rather than the hand of nature. But Schoch's analysis of the rock told a different story. The formation is composed of medium to very fine sandstones and mudstones belonging to the Yaya-Ayama group, a geological layer deposited roughly 20 million years ago during the early Miocene period. These sandstones, Schoch explained, contain numerous well-defined parallel bedding planes along which the layers easily separate. They are also crossed by sets of parallel, vertically oriented joints, natural fractures that cause the rock to break in rectangular and geometric patterns. In other words, the very qualities that make the monument look man-made, the sharp edges, the flat planes, the stepped appearance, are the same qualities that occur naturally in this type of sandstone, especially in a region as seismically active as southern Japan. Yonaguni lies squarely within the ring of fire. Earthquakes are common, and those earthquakes over thousands of years would have fractured the rock along its natural planes of weakness, creating the geometric shapes that so captivate divers and tourists. Schoch pointed out that similar formations can be found above water on the northeast coast of Yonaguni itself, where layered sedimentary rocks form impressive angular peaks and terraced hillsides that look every bit as architectural as the underwater monument. If nature can produce these shapes on land, it can produce them beneath the sea as well. And yet, Schoch was careful not to dismiss the site entirely. He concluded that while the Yonaguni monument is most likely 95% natural, parts of it may have been touched up by ancient humans. Evidence of very old habitation exists on the island, including tombs and other features carved from the bedrock in styles that echo the stepped appearance of the underwater formation. It is possible, even likely, that the ancient inhabitants of Yonaguni admired the natural monument, visited it when sea levels were lower, and perhaps modified portions of it for ceremonial or symbolic purposes. But the bulk of the structure, in Schoch's view, is the work of geology, not civilization. In 2024, a new study presented at the Association of Japanese Geographers Spring Academic Conference added further weight to the natural explanation. Researcher Hironobu Suga and his team conducted detailed underwater observations and documented active erosion processes at the site, including bedrock detachment, abrasion, and the formation of potholes of various shapes and sizes. These are exactly the kinds of processes that over millennia would produce the features seen at the monument. Neither the Japanese Agency for Cultural Affairs nor the government of Okinawa Prefecture recognizes the Yonaguni monument as an important cultural artifact. No official preservation or research effort has been undertaken by either agency. The site remains, for now, a popular dive attraction and an enduring source of debate. It is a place where the geometry of nature mimics the geometry of architecture so convincingly that even scientists cannot agree on where one ends and the other begins. And perhaps that is the real mystery, not whether the monument is man-made or natural, but how much of what we see in the deep reflects reality, and how much reflects what we want to find. While Japan's underwater monument divides researchers above the surface, the creatures that inhabit the deep ocean divide our understanding of biology itself, because in the cold, lightless waters of the abyssal zone, something remarkable happens. Life does not just survive, it grows, and in some cases it grows to proportions that seem to belong not to this world, but to the pages of mythology. The phenomenon is called deep-sea gigantism, and it is one of the most consistently observed and least fully understood patterns in marine biology. Across dozens of species and multiple branches of the tree of life, organisms living in the deep ocean tend to grow far larger than their relatives in shallower water. Giant isopods, which are related to the common woodlouse you might find under a rock in your garden, grow to nearly 20 inches long in the deep sea. Japanese spider crabs, scuttling across the abyssal plains of the Pacific, can reach a leg span of 12 feet, roughly the width of a small car. Oarfish, those serpentine ribbons of silver that surface only rarely and often in pieces, have been measured at more than 36 feet in length. And then there are the squid. For centuries sailors told stories of enormous tentacled creatures that rose from the deep to drag ships beneath the waves. The Norse called it the kraken, a beast so vast that it could be mistaken for an island. For most of recorded history, science dismissed these accounts as fantasy, the product of fear, rum, and long months at sea. But the ocean, as it so often does, had the last word. The giant squid, Architeuthis dux, is real. It lives in the deep waters of every major ocean, and for all the centuries of stories, humanity did not manage to photograph a living giant squid until 2004, when Japanese researchers Tsunemi Kubodera and Kyoichi Mori captured images of one near the Ogasawara Islands at a depth of roughly 900 meters. The animal was enormous, its tentacles stretched to nearly 26 feet, and it fought violently against the bait line, eventually losing one of its feeding tentacles in the struggle. That severed tentacle was still moving, still grasping, when it was pulled to the surface. It would be another 8 years before a giant squid was filmed alive in its natural habitat. In 2012, a joint Japanese, American and NHK expedition in the Pacific managed to capture footage of a giant squid at depth using a specially designed camera system with red light, invisible to most deep-sea creatures. The footage, broadcast worldwide, showed a shimmering silver-gold animal gliding through the blackness with an almost regal slowness, its massive eyes reflecting the faint light of the camera like mirrors. It was the first time in human history that anyone had seen a living giant squid behaving naturally in the deep ocean. And yet, for all that achievement, scientists have learned almost nothing about the animal's life, how it hunts, how it mates, how long it lives, how large it truly grows. Estimates of maximum size range from 43 to 66 feet, but without more specimens, those numbers are little more than educated guesses. The giant squid's cousin, the colossal squid, is even more elusive. Mesenocoteuthis hamiltoniae is thought to grow up to 45 feet in length and is distinguished from its cousin by the presence of rotating hooks on its tentacles instead of the suction cups found on most squid. Colossal squid inhabit the deep Antarctic waters around the Southern Ocean, and encounters with them are extraordinarily rare. In fact, it was not until 2025 that a colossal squid was filmed for the first time. The footage showed a juvenile, roughly 1 foot in length, drifting through the cold southern water. A baby. Even less is known about the colossal squid than the giant. Its maximum size, its behaviour, its range, all remain open questions. We know it exists. We have held dead specimens in our hands. And that is very nearly all we know. The reasons for deep-sea gigantism are debated, but several hypotheses carry weight. One is an extension of Bergmann's rule, which observes that organisms in colder environments tend to grow larger because bigger bodies conserve heat more efficiently. The deep ocean is cold, consistently hovering just above freezing, and a larger body would retain metabolic warmth more effectively than a small one. Another explanation involves metabolic efficiency. Larger organisms generally have slower metabolic rates relative to their body mass, which is an advantage in the food-scarce environment of the deep sea, where meals may arrive unpredictably and survival depends on making each calorie last. There is also the matter of pressure. The immense hydrostatic pressure at depth affects cellular function in ways that are still being studied, and some researchers believe it may promote slower aging and longer growth periods, allowing organisms to reach sizes impossible in the shallow sunlit waters above. And then there is the case of Leptocephalus giganteus. In 1930, a Danish researcher named Anton Brun described an unusual eel larva recovered from the deep Atlantic. It was enormous, roughly 6 feet long, translucent, and unmistakably in a larval stage of development. In most eel species, the larval form is a tiny fraction of the adult size. If Leptocephalus giganteus followed the same growth pattern, and if eel larvae are typically about 1/32nd the length of their adult form, the implication was staggering. The adult version of this creature could theoretically reach a length of nearly 200 feet, a sea serpent in all but name. Only 2 specimens have ever been studied, both larvae, both recovered decades ago. Contemporary scientists have suggested that Leptocephalus giganteus was likely misidentified, perhaps a larva of an already known species that simply does not grow much beyond its larval size. But without more specimens, without a confirmed adult form, the question remains suspended in the same darkness that hides the creature itself. What is it? How large does it get? And where, in the vastness of the deep ocean, is it hiding? If the deep can grow creatures to impossible size, what other impossibilities might it harbour? In the Gulf of Mexico, more than 3,000 feet below the surface, researchers found a body of water that defies the very definition of the word. Picture the floor of the ocean, dark, flat, featureless sediment stretching in every direction. Now picture, sitting on that floor, a pool, not a metaphorical pool, an actual lake, complete with a shoreline, a surface, and water that behaves differently from the ocean around it. That is what scientists found at the bottom of the Gulf of Mexico, roughly 3,300 feet below the waves. They called it the Jacuzzi of Despair, and it earns its name. The lake is roughly 12 feet deep and 32 feet across, modest by any measure. But what makes it extraordinary is not its size, it is its chemistry. The water inside the pool is hypersaline, far saltier than the surrounding ocean, and saturated with dissolved methane and hydrogen sulfide. The combination creates a body of water so toxic that virtually any creature that wanders into it dies almost immediately. Researchers who have visited the site in submersibles describe the shoreline of the pool as being littered with the preserved corpses of crabs, fish, and other organisms that ventured too close. Some of them appear almost pickled, suspended in the brine in eerie, lifelike poses, as though time itself had stopped at the edge of the water. Brine pools like this one form when ancient deposits of salt, buried deep beneath the seafloor, dissolve into the surrounding seawater. The resulting brine is so dense that it pools on the ocean floor rather than mixing with the water above it, creating a distinct boundary between the two liquids that is visible to the naked eye. From a submersible, it looks exactly like a lake on land, complete with ripples across its surface when disturbed by currents. The effect is surreal and deeply unsettling, a body of water within a body of water, each with its own chemistry, its own temperature, and its own rules. Despite the toxicity, life does not entirely abandon these places. Along the edges of the Jacuzzi of Despair, colonies of specialized bacteria thrive, drawing energy not from sunlight, but from the chemical reactions between the brine and the surrounding seawater. These chemosynthetic organisms form the base of a small but resilient food chain. Mussels cluster along the margins of some brine pools, feeding on the bacteria and creating what scientists have described as mussel beaches, shorelines of living shellfish ringing a toxic lake at the bottom of the sea. Similar brine pools have been found in the Red Sea and the Mediterranean, and each one supports its own unique ecosystem of extremorphals, organisms that have adapted to conditions that would kill almost anything else on Earth. These environments are of enormous interest to astrobiologists, scientists who study the possibility of life beyond Earth. The conditions inside a deep-sea brine pool, extreme salinity, toxic chemistry, total absence of sunlight, bear a remarkable resemblance to the conditions believed to exist on Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn. Both worlds are thought to harbour liquid water beneath their icy surfaces, water that may be rich in dissolved salts and chemicals. If life can survive at the edge of the Jacuzzi of Despair, the thinking goes, then perhaps life can survive beneath the ice of another world. The deep ocean, in this sense, is not just a frontier of Earth, it is a rehearsal for the exploration of the cosmos. The Gulf of Mexico holds more than toxic lakes. Its floor is a graveyard of ships spanning centuries of human history. An estimated 4,000 wrecks lie scattered across the Gulf seabed, an underwater archaeological record of exploration, commerce, conflict and catastrophe. Some of these wrecks are well documented, the remnants of warships and merchant vessels whose loss was recorded in naval logs and harbour records, but many others are anonymous. They rest in the silt without names, without histories, without anyone alive who remembers them. In May of 2019, a team of researchers from the National Oceanic and Atmospheric Administration was conducting tests with underwater drones in the Gulf when their sonar picked up a return that did not match any known wreck in the database. They directed the drone toward the signal, and what appeared on their screens was the ghostly outline of a wooden sailing vessel, roughly 124 feet long, resting on the seafloor in remarkably good condition. The hull was constructed of wood with copper sheathing, a technique common in the 18th and 19th centuries to protect against marine borers. Parts of the timber were charred, suggesting the ship had been burning when it went down. On its hull the number 2109 was faintly visible, but the researchers could not match it to any known vessel. The ship's country of origin, its name, the number of crew it carried, the purpose of its final voyage, and the circumstances of its sinking are all unknown. Marine archaeologists from across the world watched the exploration via livestream, hoping to identify some clue. None was found. The ship remains, as of today, a mystery, one of thousands resting silently beneath the warm, dark waters of the Gulf. Ships vanish, submarines disappear, and in some of the most travelled stretches of ocean on Earth, the pattern has repeated itself for longer than anyone can remember. The year 1968 was by any standard a turbulent one. Revolutions swept through cities on every continent. Wars raged in Southeast Asia and the Middle East. The space race was accelerating toward its climax, and beneath the surface of the world's oceans, something else was happening. Something that, even now, more than half a century later, has never been fully explained. In the span of a single year, 4 submarines belonging to 4 different nations had vanished, under circumstances that remain, in each case, shrouded in suspicion and incomplete answers. The first was the Alfie INS Dakar, an Israeli submarine that disappeared in the eastern Mediterranean on January the 25th, while en route from Britain to its new home port in Haifa. The Dakar was carrying a crew of 69 men. It sent a routine position report and was never heard from again. Despite one of the most extensive search operations in Israeli naval history, no trace of the submarine was found for more than 30 years. It was not until 1999 that the wreckage was finally located on the Mediterranean seabed at a depth of nearly 10,000 feet. The cause of its sinking was never conclusively determined. Just 4 days later, on January the 29th, the French submarine Minerve disappeared in the western Mediterranean, only about 25 nautical miles from its home port of Toulon. The Minerve was carrying 52 crew members and had been conducting routine exercises when it vanished. It was close enough to show that rescue should have been a matter of hours, not days, and yet the submarine was simply gone. No distress signal, no debris, no oil slick. The French Navy searched for weeks and found nothing. The wreck of the Minerve was not located until 2019, more than 50 years after it disappeared, resting on the seabed at a depth of roughly 7,600 feet. The French government has offered no public explanation for what caused the loss. In March of that same year, a Soviet submarine, K-129, vanished in the Central Pacific Ocean while on a routine patrol. The K-129 was a Gulf-class ballistic missile submarine carrying 3 nuclear-armed missiles and a crew of roughly 98 men. When the submarine failed to report in, the Soviet Navy launched a massive, but ultimately futile search. The United States, which had been tracking K-129 through its SOSUS hydrophone network, located the wreck on the Pacific floor at a depth of more than 16,000 feet. In 1974, the CIA attempted to secretly recover the submarine in an operation known as Project Azorian, using a specially built ship called the Hughes Glomar Explorer. The operation was only partially successful. Parts of the submarine were recovered, but the section containing the nuclear missiles was reportedly lost during the lift. The full details of the operation remain classified. And then, in May of 1968, the USS Scorpion, an American nuclear-powered attack submarine, disappeared in the Atlantic Ocean while returning to its home port of Norfolk, Virginia, from a Mediterranean deployment. The Scorpion was carrying 99 crew members. When it failed to arrive on schedule, the Navy launched a search that eventually located the shattered hull on the Atlantic seabed at a depth of roughly 10,000 feet, about 400 miles southwest of the Azores. Photographs of the wreckage showed the submarine had been torn apart by a catastrophic implosion. The Navy's official investigation concluded that the most likely cause was a torpedo malfunction, a scenario in which one of the ship's own weapons detonated inside the hull. But the investigation was conducted behind closed doors, and no official cause of the sinking was ever publicly announced. Some theorists, noting the geopolitical tensions of the era, have suggested that the Scorpion was the target of a Soviet attack, a retaliation for the loss of K-129. No evidence has ever confirmed that claim, but no evidence has ever disproven it either. 4 submarines, 4 nations, 1 year. The statistical improbability of such a cluster of losses has fueled speculation for decades. Were these isolated accidents, each with its own mechanical or human cause? Or was something else at work beneath the surface, some pattern or conflict that the Cold War's secrecy has kept hidden? The ocean does not answer. It simply holds the wreckage and waits. The loss of submarines in 1968 is haunting, but it is not the oldest maritime mystery by any measure. In March of 1918, during the final year of the First World War, the USS Cyclops departed Barbados bound for Baltimore, Maryland. The Cyclops was one of the largest ships in the United States Navy at the time, a massive coal carrier more than 500 feet long and displacing nearly 20,000 tons when fully loaded. It carried a crew and passengers numbering more than 300 souls. The ship never arrived. No distress signal was ever received. No wreckage was ever found. No bodies were ever recovered. To this day, the disappearance of the USS Cyclops is the single largest loss of life in United States Navy history that did not involve combat. And the cause remains entirely unknown. The Cyclops vanished in a stretch of the Atlantic Ocean that would, decades later, become one of the most famous and most feared regions on any map. Roughly 500,000 square miles of ocean, bounded by Bermuda to the north, Miami to the west, and San Juan, Puerto Rico to the south. It is known, of course, as the Bermuda Triangle. The reputation of the Bermuda Triangle is enormous, fueled by decades of books, documentaries, television specials, and internet speculation. Hundreds of ships and aircraft have been reported lost in the area over the past century, some under genuinely puzzling circumstances. In December of 1945, 5 United States Navy torpedo bombers, known collectively as Flight 19, departed Fort Lauderdale on a routine training mission and were never seen again. The flight leader radioed that his compasses had malfunctioned and that he could not determine his position. A search aircraft sent to find them also vanished. No wreckage from any of the 6 aircraft was ever recovered. Stories like these have cemented the Bermuda Triangle's place in popular mythology, but the scientific reality is considerably less dramatic. The National Oceanic and Atmospheric Administration has stated plainly that there is no evidence the Bermuda Triangle is any more dangerous than any other comparable stretch of ocean. The United States Coast Guard has echoed that position, noting that no extraordinary factors have ever been identified in connection with the area. The triangle sits at the intersection of some of the busiest shipping and aviation routes in the world, and when adjusted for the volume of traffic passing through it, the rate of incidence is not statistically unusual. That said, NOAA acknowledges several natural factors that can make navigation in the area challenging. The region is prone to sudden and severe weather, including hurricanes that can develop with little warning. The Gulf Stream, a powerful ocean current that flows through the triangle, can create rapid and unpredictable changes in sea conditions. The numerous islands and shallow shoals of the Caribbean make navigation tricky, especially in poor visibility. And NOAA has noted that the area may produce localized magnetic anomalies that could cause compasses to point toward true north rather than magnetic north, potentially disorienting pilots and sailors who do not account for the difference. There is even a hypothesis involving methane gas. The seafloor beneath parts of the triangle contains large deposits of methane hydrate, a frozen form of natural gas trapped in the sediment. If a large quantity of this gas were to erupt suddenly from the seafloor, it could reduce the density of the water above it, causing a ship to lose buoyancy and sink within seconds. Laboratory experiments have demonstrated that this is physically possible, though no confirmed case of such an eruption causing a maritime disaster has ever been documented. The Bermuda Triangle, in the end, is likely more a product of storytelling than of supernatural forces. Human beings are pattern-seeking creatures. We notice clusters of events and assign them meaning, even when the clustering is within the range of statistical chance. The ocean is a dangerous place. Ships and planes are lost in every ocean, every year, for reasons ranging from mechanical failure to human error to weather. The Bermuda Triangle simply has a better publicist than the rest of the sea. But if the Atlantic has its triangle, the Pacific has its own zone of dread, and this one fewer people know about. In the western Pacific Ocean, between the coast of Japan, the Bonin Islands, and the island of Taiwan, lies a stretch of water that Japanese sailors have feared for centuries. It is known by several names: the Devil's Sea, the Dragon's Triangle, the Pacific Bermuda Triangle. Like its Atlantic counterpart, it is associated with the unexplained disappearance of ships and aircraft. Unlike the Bermuda Triangle, however, the Devil's Sea sits atop some of the most geologically violent terrain on the planet. The region is riddled with submarine volcanoes, deep ocean trenches, and powerful seismic faults. Eruptions, earthquakes, and rogue waves are not legends here. They are documented recurring events. The most famous incident associated with the Devil's Sea occurred in 1952, when the Japanese government sent a research vessel, the Kayo Maru No. 5, to investigate reports of unusual volcanic activity in the region. The ship carried a crew of 31 scientists and sailors. It sailed into the area and was never seen again. A subsequent search found fragments of the vessel, suggesting it had been destroyed by a sudden volcanic eruption or an associated underwater shockwave. The Japanese government subsequently designated portions of the area as a danger zone, advising ships to avoid it when possible. During the Second World War, the United States Navy lost more than 20 submarines in the waters of the Western Pacific, many of them in or near the region associated with the Devil's Sea. While most of these losses can be attributed to enemy action, depth charges, mines, and aerial attacks, a number remain unexplained. Submarines that simply stopped communicating and were never found. The Pacific is not a forgiving ocean. Its storms are immense, its currents are relentless, and its depths, in places, exceed anything found in the Atlantic. The Devil's Sea may or may not be more dangerous than other stretches of the Pacific, but the combination of extreme weather, active volcanism, and a long history of loss gives the region a reputation that is, at the very least, well earned. From cursed stretches of ocean to the ocean's most alien ecosystems, our journey now takes us to a place where the rules of life as we understand them simply do not apply. A place where the sun has never shone, where the temperature of the water can exceed that of molten lead, and where life does not merely survive, it flourishes. In 1977, a team of geologists aboard the research submersible Alvin descended to the ocean floor near the Galapagos Rift, a volcanic spreading centre in the eastern Pacific where two tectonic plates are slowly pulling apart. They were looking for evidence of hydrothermal activity, vents in the seafloor where superheated water escapes from the Earth's interior. What they found changed the course of biology forever. As Alvin approached the rift zone, the temperature of the surrounding water began to climb. Then through the submersible's viewport, the scientists saw something no human had ever witnessed. Columns of superheated, mineral-laden water were erupting from cracks in the ocean floor, billowing upward in dark, roiling clouds. The water pouring from these vents was staggeringly hot, reaching temperatures of more than 400 degrees Celsius, well above the boiling point of water at the surface. It remained liquid only because of the immense pressure at depth, which prevents it from turning to steam. The minerals dissolved in the fluid, iron, copper, zinc, manganese, precipitated instantly upon contact with the frigid surrounding seawater, forming towering chimneys of dark metallite deposits. The scientists named them black smokers, and they looked like nothing so much as factory smokestacks rising from the floor of an alien world. But what stunned the researchers was not the geology, it was the life. Clustered around the base of each vent, in water that should have been lethal to any organism, were dense colonies of creatures that had no business being there. Giant tube worms, some more than 6 feet long, swayed in the hydrothermal current, their bright red plumes extending from white, tubular casings. Mats of bacteria, thick and pale, carpeted the surrounding rock. Clams the size of dinner plates sat half buried in the sediment. Crabs picked their way through the colonies, and blind shrimp, their eyes replaced by heat-sensing organs, swarmed the vent openings. None of these organisms depended on sunlight. In the deepest, darkest reaches of the ocean, where photosynthesis is impossible, an entirely different form of life had evolved. Instead of using the energy of the sun to convert carbon dioxide into organic matter, the bacteria at the base of these ecosystems use chemical energy, drawing sustenance from the hydrogen sulfide and other compounds pouring out of the vents. This process, known as chemosynthesis, was not merely a curiosity, it was a fundamental discovery, proof that life on Earth did not require the sun. The implications rippled outward from marine biology into astrobiology, into the study of the origins of life, and into the search for life beyond Earth. If organisms could thrive in the pitch darkness of the ocean floor, sustained by nothing more than the chemical energy of the planet itself, then the definition of habitability needed to be rewritten. Since 1977, hydrothermal vents have been found on virtually every ocean ridge system on the planet, and with each new discovery, the diversity of vent life has expanded in astonishing ways. In 2010, researchers discovered the Von Dam vent field in the Caribbean Sea. Unlike most hydrothermal vents, which build their chimneys from sulfide compounds, the structures at Von Dam are composed of talc, the same magnesium silicate mineral found in baby powder. Some of these talc chimneys tower as high as 75 meters above the seafloor, elegant pale spires rising from the volcanic darkness. The Mid-Cayman spreading centre, where Von Dam was found, is part of a mid-ocean ridge system of which roughly 75% remains unexplored. Over 500 new animal species have been discovered at hydrothermal vents within this ridge system alone, many of them found nowhere else on Earth. Further north, in the Arctic Ocean, the Gackel Ridge stretches between Greenland and Siberia. It is the deepest mid-ocean ridge in the world, reaching depths of up to 3 miles, and it remained entirely unexplored until the early 2000s. In 2003, researchers found the first Arctic hydrothermal vents there, and the biological communities surrounding them were unlike anything found in warmer waters. The isolation of the Gackel Ridge, cut off from other ocean basins by geography and current, means that the organisms living at its vents are likely endemic species, unique to that one location on Earth. Density measurements showed that life around these vents is up to 100,000, times more concentrated than in the surrounding open ocean. In 2007, the Agave expedition to the Gakkel Ridge discovered vast deposits of pyroclastic volcanic material on the seafloor, glassy shattered rock produced by explosive underwater eruptions. The material formed strange glass-like structures across the seabed, evidence of a level of volcanic violence that no one had expected to find in the Arctic. But perhaps the most extraordinary discovery, connected to extreme ocean environments, came not from a vent, but from beneath the ice. In the frigid waters of Antarctica, a few intrepid research teams have drilled hundreds of meters through the Ross Ice Shelf, the largest floating body of ice on Earth, and lowered cameras and instruments into the water below. What they found astonished them. Living beneath the ice, in perpetual darkness and near freezing temperatures, were fish, crustaceans, sea anemones, clinging to the underside of the ice shelf, and strange upside-down swimming fish that appeared to navigate by senses no one fully understands. No one knows how these organisms reach such an isolated environment, or how they sustained themselves in conditions so extreme. But the discovery has enormous implications beyond Earth. The conditions beneath the Antarctic ice shelf closely resemble those believed to exist on Europa, where a global ocean is thought to lie beneath a thick crust of ice. If life can survive under the ice of Antarctica, it might survive under the ice of Jupiter's moon. The deep ocean, it turns out, may be the best laboratory we have for understanding whether we are alone in the universe. Life persists where we least expect it. But not everything beneath the surface is alive. Some of the ocean's strangest residents are the phantom islands that appear on maps, are recorded in the logs of experienced sailors, and then vanish from the face of the earth as though they were never there. Throughout the history of cartography, islands have appeared on charts that, upon investigation, turn out not to exist. They are known as Phantom Islands, and their stories are among the quietest and most unsettling mysteries of the sea. An island is, by definition, a permanent thing. It is land. It is solid. It should not simply cease to be. And yet, time and again, islands that were mapped, named, and in some cases visited by multiple expeditions have proven, upon later inspection, to be absent. One of the most famous cases is Bermeja, a small island that appeared on maps and nautical charts of the Gulf of Mexico from the 16th century onward. Spanish colonial maps marked it clearly, placing it roughly 100 miles north of the Yucatan Peninsula. For centuries it was accepted as a real landmass, a reference point for navigation in the Western Gulf. But in 2009, when Mexican surveyors set out to locate the island, they found nothing. The coordinates where Bermeja should have been contained only open water. The island had apparently vanished. Conspiracy theories emerged almost immediately. Some suggested that the United States government had destroyed the island to expand its territorial claims over the oil-rich seabed of the Gulf. Others proposed that the island had been swallowed by rising sea levels or eroded away by storms. The simplest explanation, and likely the correct one, is that Bermeja never existed at all, that it was a cartographic error, a misplotted coordinate that was copied from map to map for hundreds of years without anyone bothering to verify it. But the mystery lingers, because no one has ever proven exactly how the island came to appear on so many charts in the first place. A more recent case involves Sandy Island, which appeared on maps of the Coral Sea between Australia and New Caledonia for more than a century. It was plotted on Google Maps and Google Earth. It appeared in official nautical databases. And yet when an Australian research vessel sailed through the area in 2012, the crew found nothing but deep, open ocean. The island did not exist. It had never existed. It was like Bermeja, a phantom, a piece of land that lived only on paper and in pixels. The Sargasso Sea is not a phantom, but it is perhaps the ocean's strangest legitimate body of water. It is the only sea on Earth that is defined not by land boundaries, but by ocean currents. Located in the North Atlantic, the Sargasso Sea is bounded on all sides by four major current systems: the Gulf Stream to the west, the North Atlantic Current to the north, the Canary Current to the east, and the North Atlantic Equatorial Current to the south. The result is a vast, calm, elliptical region of water that sits relatively still while the currents rotate around it like a slow, liquid carousel. The surface of the Sargasso Sea is covered with enormous mats of free-floating sargassum seaweed, golden brown rafts of vegetation that can stretch for miles and support entire ecosystems of small fish, crabs, shrimp, and sea turtles. Historically, the Sargasso Sea was feared by sailors. Ships becalmed in its windless centre could drift for days or weeks, their hulls gradually fouled by barnacles and seaweed, their crews growing desperate. The image of a ship trapped in a sea of weed, its sails hanging limp, its crew slowly dying of thirst, became one of the most enduring metaphors of maritime dread. Islands that were never there, seas that hold ships like insects in amber, and beneath it all, a world of life so vast and so hidden that we are only now beginning to glimpse its true scale. Between the sunlit surface waters, where most marine life thrives, and the pitch-black abyss of the deep ocean, lies an intermediate realm that scientists call the mesopelagic zone. It extends from roughly 200 metres down to about 1,000 metres, a twilight region where the last traces of sunlight fade into darkness. For most of the history of oceanography, this zone was treated as a kind of biological desert, a dim, empty corridor between the productive surface and the exotic deep. That assumption turned out to be spectacularly wrong. The mesopelagic zone, now commonly known as the Twilight Zone, is believed to contain more fish than the rest of the ocean combined. A 2014 research paper estimated that the biomass of mesopelagic fish may be 10 times greater than previous calculations had suggested, potentially making it the largest concentration of animal life on Earth. The zone is home to an extraordinary collection of organisms, many of which have never been studied in detail. Bioluminescent creatures generate their own light in the darkness, flickering and pulsing in patterns that serve as camouflage, communication, or lures for prey. Among the more remarkable inhabitants are siphonophores, colonial organisms made up of hundreds of specialized individuals that function together as a single body. Some siphonophores can grow to lengths of 150 feet, longer than a blue whale, making them the longest animals on the planet. But perhaps the most astonishing feature of the Twilight Zone is what happens every single day within it. As the sun sets, billions upon billions of organisms begin a vertical migration from the deep toward the surface, rising hundreds of meters through the water column to feed on the plankton and smaller organisms that live near the top of the ocean. When dawn approaches, they descend again, retreating into the darkness to avoid predators. This daily migration is the largest movement of animals on Earth, and it happens every day, in every ocean, without pause. The sheer biomass involved is difficult to comprehend. Fish, squid, jellyfish, crustaceans, and worms all participate, moving in dense living columns that can be detected by sonar as a distinct layer in the water. In fact, this biological layer was first detected during the Second World War, when Navy sonar operators noticed a mysterious secondary bottom, a false floor that appeared to rise toward the surface each night and sink again each morning. They called it the deep scattering layer, and for years no one knew what it was. It was only later, as marine biologists began studying the mesopelagic zone in earnest, that the truth emerged. The false bottom was not a geological feature, it was alive. An entire stratum of the ocean, hundreds of meters thick, made of trillions of living organisms, moving together in a rhythm as old as the ocean itself. Despite its staggering biological importance, the Twilight Zone remains one of the least understood ecosystems on Earth. Its depth makes it difficult and expensive to study. The organisms that live there are often fragile, falling apart when brought to the surface, and the sheer volume of the zone, covering the entire global ocean at depth between 200 and 1,000 meters, means that studying even a small fraction of it would require decades of sustained effort. What we do know suggests that the mesopelagic zone plays a crucial role in regulating the planet's climate. The organisms that migrate vertically each day transport enormous quantities of carbon from the surface to the deep, effectively pumping carbon dioxide out of the atmosphere and locking it away in the ocean's interior. If this biological carbon pump were to falter, the effects on global climate could be significant. The twilight zone, in other words, is not just a curiosity. It is a vital organ of the planet's life support system, and we are only beginning to understand how it works. The ocean's apex predators are not as invulnerable as we once believed, and in the waters off one of the most famous coastlines in the world, something has been hunting the hunters. Since 2017, something disturbing has been happening along the coast of South Africa. Great white sharks, the ocean's most formidable apex predators, have been washing ashore dead. That alone would not be particularly unusual. Sharks die. They beach themselves. They succumb to disease or old age or entanglement with fishing gear. But these sharks were not simply dead. They had been surgically opened, their massive livers removed with a precision that stunned marine biologists. The wounds were clean, almost clinical, and in case after case the liver was the only organ missing. Everything else, the heart, the stomach, the muscle, was left untouched. The shark liver is an extraordinary organ. In a great white, it can weigh more than 100 pounds and accounts for a significant portion of the animal's total body weight. It is rich in squalene, a highly energy-dense oil that the shark uses for buoyancy and as a metabolic fuel reserve. To anything capable of extracting it, a shark liver is one of the most nutritious meals available in the ocean. The question was not why something would want a shark liver. The question was what, exactly, was powerful enough, skilled enough, and precise enough to take one from a living great white. The answer, when it came, was both remarkable and terrifying. Researchers identified 2 male orcas, killer whales, that had been increasingly active in the waters off South Africa's Western Cape. These 2 individuals, known to marine biologists by the names port and starboard, due to the distinctive flopping direction of their dorsal fins, were observed in the vicinity of the strandings on multiple occasions. Orcas are known to be intelligent, highly social and capable of developing specialized hunting techniques that are passed down through generations. Some orca populations specialize in hunting seals, others target herring or salmon. And in various parts of the world, orcas have been documented killing sharks, including great whites, by flipping them upside down to induce a state of paralysis called tonic immobility, then biting into them to extract the liver. What made the South African cases exceptional was the scale and the consequence. The arrival of port and starboard in the waters around False Bay and Gunspai, 2 areas historically famous for their dense populations of great white sharks, triggered something that no one had ever observed before. The great whites fled, not just a few of them, nearly all of them. Shark monitoring stations along the Western Cape recorded a dramatic, sustained decline in great white sightings that coincided precisely with the presence of the 2 orcas. Areas that had been reliably patrolled by great whites for decades were suddenly empty. The apex predator of the ocean had met something it feared more, and it had chosen to leave rather than fight. The broader implications are still being studied. The sudden absence of great whiteys from their traditional territories has ripple effects throughout the marine ecosystem. Without the top predator to regulate their numbers, populations of smaller sharks and seals may shift in unpredictable ways. Some researchers worry that the great whites may not return for years if they return at all. The situation is a stark illustration that even the most dominant creatures in the ocean are not beyond challenge, and that the balance of the marine food web is far more fragile than it appears. The orca killings are well documented, but they are not the only predation mystery involving great white sharks. In 2003, an Australian filmmaker named Dave Riggs tagged a 9-foot-long female great white shark off the coast of Australia. The tag, a pop-up satellite archival device, was designed to record the shark's depth temperature and movement patterns over time. For several months, the data came back as expected. The shark was behaving normally, cruising through its usual territory, diving and surfacing in predictable rhythms. And then, abruptly the data changed. The tag recorded a sudden dramatic plunge to roughly 1,900 feet, far deeper than a great white would typically dive. At the same time, the temperature recorded by the sensor spiked from 46 degrees Fahrenheit to 78 degrees, a rapid and extreme increase consistent with the tag having entered the digestive system of a warm-bodied animal. The shark, it appeared, had been attacked and consumed by something significantly larger than itself. Shortly afterward, the tag detached and washed ashore. The question of what ate the shark has never been answered definitively. Some researchers suggested it may have been a much larger great white, as the species is known to be cannibalistic in certain circumstances. Others proposed a large mako shark, or an unusually bold orca. The temperature data pointed to a warm-blooded predator, which narrows the field considerably. But without a direct observation, the identity of the animal that consumed a 9-foot great white remains an open question, a reminder that the food chain of the open ocean extends further and higher than we often assume. If the creatures of the upper ocean are defined by their power, the creatures of the deep are defined by something altogether different: light, or rather, the absence of it. Below the mesopelagic twilight zone lies the bathypelagic zone, the midnight zone, a realm of permanent, absolute darkness that extends from roughly 1,000 meters to 4,000 meters below the surface. No sunlight reaches the midnight zone. The only illumination comes from the organisms themselves, and they produce it in abundance. Bioluminescence, the ability to generate light through chemical reactions within the body, is the most common form of communication in the deep ocean. It is estimated that more than 75% of all organisms living between the surface and the deep sea floor are capable of producing light. In the midnight zone, that percentage is even higher. Nearly everything glows. Fish carry lantern-like organs called photophores along their bodies, arranged in species-specific patterns that serve as identification badges in the darkness. Some use their light to attract prey, dangling luminous lures in front of their mouths like anglerfish. Others use it defensively, releasing clouds of bioluminescent mucus to confuse predators while they escape. Some deep-sea squid can produce light in complex, rapidly changing patterns across their entire bodies, a visual language that researchers are only beginning to decode. The chemistry of bioluminescence is elegant in its simplicity. Most organisms produce light through the reaction of a molecule called luciferin with an enzyme called luciferase. When the two combine in the presence of oxygen, energy is released in the form of photons. The light produced is almost always blue or green, because these wavelengths travel furthest through seawater. Red light, which is absorbed quickly by water, is virtually absent in the deep ocean. This means that creatures capable of seeing red, such as certain species of dragonfish, have a secret weapon. They can project red light as a kind of invisible searchlight, illuminating prey without being detected. The dragonfish belonging to the family Stomidae is one of the midnight zone's most effective predators. Small, rarely more than 6 inches long, it carries a bioluminescent barbel beneath its chin and photophores along its belly. But its most remarkable feature is its ability to see in the far red spectrum, a capacity that is almost unique among deep-sea fish. Using a specialized visual pigment derived from chlorophyll, which it obtains through its diet, the dragonfish can detect wavelengths of light that are invisible to virtually everything else in its environment. It is, in effect, hunting with night vision goggles that no other animal can see. The midnight zone is also home to the vampire squid, an animal whose name is far more dramatic than its behaviour. Despite its sinister appearance, the vampire squid is a gentle creature that feeds on marine snow, the slow, continuous rain of organic particles that drifts down from the surface. It lives at oxygen minimum zones, layers of water where dissolved oxygen is so low that most organisms cannot survive. The vampire squid has adapted to these conditions by developing the lowest metabolic rate of any cephalopod, breathing through enormous gills relative to its body size, and producing blood pigment that binds oxygen with exceptional efficiency. It does not hunt, it does not chase, it simply drifts through the dark, catching flakes of debris and sticky filaments that it slowly reels in and consumes. It is one of the most ancient cephalopod lineages alive, having survived virtually unchanged for hundreds of millions of years, and there are the siphonophores, those extraordinary colonial organisms that can stretch to lengths exceeding 150 feet. A siphonophore is not a single animal, but a colony of specialized individuals, each genetically identical but functionally different. Some individuals form the swimming bell that propels the colony through the water. Others form the feeding polyps that capture prey. Others form the reproductive organs. Still others form the bioluminescent organs that light the colony's way through the dark. When disturbed, a siphonophore can produce a dazzling cascade of blue light that ripples along its entire length, a defensive display designed to startle predators. The effect, captured on film by deep-sea ROVs, is breathtaking, a living ribbon of light unfurling in the blackness like a slow-motion firework. In 2020, researchers from the Schmidt Ocean Institute filmed a siphonophore in the waters off Western Australia that measured an estimated 150 feet in length, longer than a blue whale. The colony was arranged in a coiled spiral, a feeding configuration that allowed it to sweep a large volume of water for prey. It was, at the time of its discovery, the longest biological structure ever recorded, and it was found living in complete darkness, in a part of the ocean that no human had ever visited before. The midnight zone covers more volume than any other ocean layer. It is, by sheer physical extent, the largest living space on Earth, and yet we know almost nothing about what lives in most of it. The organisms we have catalogued represent a tiny fraction of what is likely there. Every submersible dive, every ROV deployment, every camera drop into the midnight zone returns with footage of creatures that have never been seen before. Animals without names, without classifications, without any context in the scientific literature. They drift past the cameras and disappear back into the dark, leaving behind only the question of what else is down there. The deep ocean does not merely contain life, it contains the overwhelming majority of life on Earth. We simply have not found it yet, and that brings us, perhaps inevitably, to the question of what we do know about our oceans, and what remains, stubbornly and almost incomprehensibly, unknown. Before we explore what remains undiscovered, it is worth pausing to consider a mystery so fundamental that it underpins everything else we have discussed tonight. A question that, despite centuries of scientific inquiry, has never been fully resolved. Where did all this water come from? The Earth is roughly 4.5 billion years old, and for most of its existence, it has been a water world. The oceans contain approximately 332 million cubic miles of water, a volume so immense that it defies easy comprehension. If you were to spread that water evenly across the entire surface of the Earth, including all the continents, it would form a layer more than 8,000 feet deep. That is a staggering quantity of a single substance, and its presence on this particular planet, at this particular distance from the Sun, in this particular quantity, is one of the great coincidences of our solar system. No other planet that we know of has liquid water on its surface, and science is still not entirely certain how Earth got so fortunate. The theories fall broadly into two categories. The first is that the Earth formed in a region of space where water was already present, trapped within the minerals and rocks that accreted to form the planet during the earlier stages of the solar system's development. In this scenario, the water was essentially baked into the planet from the beginning, locked inside hydrated minerals deep within the Earth's interior and gradually released to the surface through volcanic outgassing over hundreds of millions of years. There is good evidence for this view. Many of the most common minerals in the Earth's mantle olivine, pyroxene, and certain forms of garnet, are capable of incorporating water molecules into their crystal structure at high temperatures and pressures. Laboratory experiments have shown that the mantle could theoretically hold several times more water than all the oceans combined, raising the possibility that the water on the surface is merely a fraction of what the planet actually contains. The second theory proposes that the Earth formed in a region of the solar system that was too hot for water to exist in its liquid or ice form, and that the oceans were delivered later by external sources. The leading candidates are comets and asteroids, particularly a class of meteorites known as carbonaceous chondrites, which contain significant amounts of water trapped within their mineral structure. Studies of the isotopic composition of water in these meteorites have shown that, in some cases, the ratio of heavy hydrogen to normal hydrogen matches the ratio found in Earth's oceans, suggesting a common origin. The idea is that during a period of intense bombardment early in Earth's history, roughly 3.8 to 4.1 billion years ago, comets and water-rich asteroids rained down on the planet in sufficient quantities to fill the oceans. Both theories have their strengths and their problems, and the truth may involve a combination of the two. What is clear is that the presence of liquid water on Earth is not something that can be taken for granted. It required a very specific set of conditions: the right distance from the sun, the right atmospheric pressure to keep the water liquid, the right magnetic field to protect the atmosphere from solar wind, and enough geological activity to cycle water between the interior and the surface. Change any one of those variables and the oceans would not exist, and without the oceans neither would we. The water that fills the ocean basins does not simply sit there. It moves, constantly, relentlessly, and on a scale that shapes the climate of the entire planet. The ocean is not a bathtub. It is a vast, three-dimensional conveyor system that transports heat, salt, nutrients, and dissolved gases from one hemisphere to another, from the surface to the abyss and back again, in a cycle that takes roughly 1,000 years to complete. This system is known as the thermohaline circulation, sometimes called the global ocean conveyor belt, and it is driven by differences in water temperature and salinity. In the North Atlantic near Greenland and Iceland, cold winter air chills the surface water and causes sea ice to form. When seawater freezes, it leaves most of its salt behind, making the remaining liquid denser and heavier. This cold, salty water is so dense that it sinks rapidly to the ocean floor, plunging thousands of meters in powerful downwelling currents that pull surface water after them like a drain pulling water from a bathtub. The sinking water then spreads southward along the bottom of the Atlantic, eventually reaching the Southern Ocean, where it joins a vast slow-moving current that circulates around Antarctica and feeds into the Indian and Pacific Oceans. In those warmer basins, the deep water gradually rises back toward the surface, warmed by equatorial heat and mixed upward by wind and tidal forces. It then flows back toward the Atlantic as surface current, completing the loop. The entire cycle, from the sinking of cold water in the North Atlantic to its return as warm surface current, is estimated to take approximately 1,000 years. The water that is sinking near Greenland today will not return to the surface for a millennium. The thermohaline circulation is enormously important for global climate. The warm surface currents that flow northward through the Atlantic, particularly the Gulf Stream and the North Atlantic Drift, carry vast quantities of heat from the tropics to northern Europe. Without this heat transport, the climate of Western Europe would be dramatically colder, perhaps by as much as 10 degrees Celsius. London, Paris, and Berlin would experience winters more like those of Labrador or northern Siberia, despite being at similar latitudes. The thermohaline circulation is, in effect, the central heating system of the northern hemisphere, and it is not as stable as it might seem. Climate scientists have warned that the influx of fresh water from melting Arctic ice and the Greenland ice sheet could disrupt the thermohaline circulation by reducing the salinity of the surface water in the North Atlantic. If the water is not salty enough, it will not sink, and if it does not sink, the conveyor belt slows or stops. Paleoclimate records show that this has happened before, roughly 12,000 years ago. At the end of the last ice age, a massive pulse of fresh water from melting glaciers shut down the circulation in the North Atlantic, triggering a sudden and severe cooling event known as the Younger Dryas that lasted more than 1,000 years. The possibility that modern climate change could trigger a similar disruption is one of the most serious and least predictable threats facing the global climate system. Beneath the slow, majestic flow of the thermohaline current, the ocean floor holds records of human history as well. The deep sea is in many ways the greatest archaeological archive on the planet. The cold, dark, oxygen-poor conditions of the deep ocean preserve materials that would have been destroyed long ago on land. Wooden ships, fabric, leather, metal, even paper can survive for centuries in the still waters of the abyss, and the sheer number of vessels that have sunk over the millennia means that the ocean floor is littered with the remains of human endeavour, on a scale that no terrestrial archaeological site can match. Consider the numbers. It is estimated that there are more than 3 million shipwrecks scattered across the world's ocean floors. Only a tiny fraction of these have ever been located, and an even smaller fraction have been explored. Many lie at depths that are, even with modern technology, extremely difficult to reach. They span the entire history of human seafaring, from ancient Egyptian reed boats and Roman grain ships to medieval cargo vessels, colonial warships and modern submarines. Each one is a time capsule, sealed by the ocean at the moment of its sinking and preserved in conditions that no museum could replicate. One of the most famous deep-sea archaeological discoveries occurred in 1985, when a team led by Robert Ballard located the wreck of the RMS Titanic on the floor of the North Atlantic at a depth of roughly 12,500 feet. The Titanic, which sank in April of 1912 after striking an iceberg, was found in two large sections surrounded by a vast debris field of personal belongings, ship fittings and structural fragments. The images that Ballard's team brought back stunned the world, the ship's bow jutting from the sediment like a monument, its grand staircase open to the black water above, its deck draped in rusticles, the strange icicle-like formations of iron-eating bacteria that are slowly consuming the hull. But the Titanic is far from the deepest or the oldest wreck that has been explored. In the Mediterranean, archaeologists have discovered ancient vessels from the Roman and Greek periods at depths exceeding 300 metres, their cargoes of amphorae, coins and trade goods preserved almost perfectly by the cold still water. In 2016, researchers from the Black Sea Maritime Archaeology Project found a remarkably intact medieval trading vessel at the bottom of the Black Sea at a depth of more than 2,000 metres. The ship, estimated to be roughly 800 years old, was in such extraordinary condition that its mast, rudder and deck structures were still visible, preserved by the anoxic, oxygen-free conditions of the Black Sea's deep water. And in the Gulf of Mexico, that underwater graveyard we visited earlier, the discovery of unknown wrecks continues at a steady pace. Each one tells a fragment of a story. A ship that caught fire and sank in the 19th century, its copper sheathing still gleaming faintly in the submersible's lights. A vessel of unknown origin, with a number painted on its hull that matches no record in any maritime archive. A collection of objects scattered across the seabed that may have come from a single catastrophic event whose details have been lost to time. The ocean is a patient archivist. It collects everything, it discards nothing, and it does not label its exhibits. For all the advances in marine archaeology, the vast majority of the ocean's wrecks will never be found. They lie too deep, in waters too remote, in regions where no one has any reason to look. And yet, they are there, thousands of ships, millions of objects, an entire library of human history, written in wood and iron and bone, resting quietly on the floor of the world's oceans, waiting for someone to come and read it. Or not. The ocean does not care whether we find them. It simply holds them, as it holds everything, in patient, silent darkness. But the wrecks are only a small part of what lies undiscovered beneath the waves. As we approach the end of our journey tonight, it is worth considering just how much of the ocean remains, in the most fundamental sense, unknown. Not in the way that a locked room is unknown, where we at least know the room exists and can imagine what might be inside it, but in a deeper, more unsettling way. Unknown as in we have not even looked yet. Unknown as in we do not know what we do not know. The ocean's greatest mystery is not any single creature or sound or structure. It is the ocean itself, its sheer incomprehensible vastness, and the humbling realization that we have barely begun to explore it. As of June of 2024, the Global Seabed 2030 project, an international effort launched by the Nippon Foundation and the General Bathymetric Chart of the Oceans, reported that only 26.1% of the Earth's ocean floor had been mapped using modern high-resolution sonar technology. That number represents a significant improvement over previous decades, when the figure was closer to 5 or 6%. But it also means that nearly 3/4 of the planet's seafloor remains, at best, a rough estimate. The satellite-derived bathymetry that covers the rest of the ocean can detect features larger than about 3 miles across, but anything smaller, seamounts, ridges, hydrothermal vents, canyons, and certainly shipwrecks, is invisible. We know those features are there because every time we look closely at a patch of ocean floor that was previously unsurveyed, we find them. The question is not whether there are more discoveries waiting. The question is how many, and what they might change about our understanding of the planet. The pace of discovery has, if anything, accelerated in recent years. In 2019, a team of Japanese archaeologists using artificial intelligence to analyze satellite and aerial imagery of the Nazca Desert in Peru identified 143 previously unknown geoglyphs, the enormous ancient drawings etched into the desert surface. That same year, a similar approach was being applied to the ocean. AI-driven analysis of sonar data has begun to reveal features on the seafloor that human analysts might have overlooked, subtle patterns in the topography that suggest volcanic activity, biological accumulation, or geological structures of unknown origin. In the fall of 2023, during the Seascape Alaska 5 expedition conducted by the National Oceanic and Atmospheric Administration, scientists operating a remotely operated vehicle on the seafloor made a discovery that no one could explain. Resting on the ocean floor at considerable depth was a small, perfectly spherical object roughly 4 inches in diameter. It was gold in colour, smooth, and appeared to be organic in origin, though its exact nature could not be determined from a visual inspection alone. The ROV carefully collected the orb and brought it to the surface, where it was preserved for laboratory analysis. Initial examination suggested it might be an egg casing of some kind, or perhaps a sponge, but its precise identity has not been confirmed. The gold orb of the Alaskan seafloor became briefly a minor sensation, a symbol of how even a routine scientific expedition can return with something that defies immediate classification. In 2016, during the Hohonu Moana expedition in the deep waters around Hawaii, NOAA-SOA's remotely operated vehicle, Deep Discoverer, was exploring the seafloor at a depth of 4,290 meters, roughly 14,000 feet, when it encountered a small, pale creature hovering just above the sediment. The animal was an octopod, a member of the octopus family, but it was unlike any species that had been documented before. Its body was almost entirely white, with a smooth, rounded mantle and short, stubby arms. It had no fins, no colour, and no apparent markings. It looked, more than anything, like a small ghost drifting through the abyss. The scientists watching the live feed from the surface immediately recognized that they were looking at something new. The octopod was later nicknamed Casper, after the cartoon ghost, and the footage went viral, turning the little creature into an unlikely celebrity. Scientists believe it represents not only a new species, but possibly a new genus of octopod entirely. At the depth where it was found, it is the deepest confirmed sighting of an incirate octopod, a group that includes most of the familiar shallow water octopuses, and yet despite its fame, virtually nothing is known about Caspar's biology, its diet, its lifespan, or how it survives in conditions of extreme pressure and near total darkness. It appeared on camera for a few brief minutes, and then it vanished back into the deep, leaving behind only the footage and a host of unanswered questions. These individual discoveries, striking as they are, represent the smallest fraction of what is out there. Every major oceanographic expedition that deploys cameras or sampling equipment in previously unexplored waters returns with observations of organisms that have never been seen before. Many of these sightings are of creatures that cannot be captured, either because they are too fragile to survive the change in pressure during ascent, or because the ROV was not equipped for collection. They exist only as video recordings, brief glimpses of animals that may not be seen again for years or decades, if ever. Some have been formally described and named on the basis of video evidence alone, a practice that would have been unthinkable in traditional taxonomy, but has become necessary given the realities of deep-sea exploration. Others remain unnamed, floating in databases as unidentified organisms, catalogued by depth and location, but otherwise unknown. The scale of the unknown is staggering. A frequently cited estimate suggests that as many as 2/3 of all marine species have not yet been discovered. Some researchers place the number even higher. The deep ocean, which covers more of the Earth's surface than all the continents and shallow seas combined, has been sampled in only the most cursory way. Entire mountain ranges exist on the seafloor that have never been surveyed. Vast plains of abyssal sediment stretch for thousands of miles in regions where no camera has ever descended. Submarine canyons, some as deep and dramatic as the Grand Canyon, cut through the continental shelves of every major landmass, and many of them have never been explored. The ocean is not just big, it is big in a way that resists comprehension, a way that makes the sum total of human exploration seem like a drop of water in a bucket that extends beyond the horizon in every direction. And now, as the 21st century advances, a new chapter in the story of the ocean is beginning to unfold. Deep-sea mining, once a theoretical concept discussed in academic papers and science fiction novels, is becoming a commercial reality. The seafloor, particularly in the abyssal plains of the Central Pacific, is strewn with deposits of polymetallic nodules, potato-sized lumps of mineral ore that contain high concentrations of manganese, nickel, cobalt, and copper. These metals are essential for the production of batteries, electronics, and renewable energy technologies, and as demand for them grows, the economic incentive to harvest the ocean floor is becoming irresistible. The International Seabed Authority, an organization established under the United Nations Convention on the Law of the Sea, has issued dozens of exploration licenses to countries and companies seeking to map and sample the mineral deposits of the deep ocean. Several nations, including China, South Korea, and various European states, have invested heavily in the development of deep-sea mining technology. Prototype systems have been tested, machines capable of scooping or vacuuming nodules from the seafloor and transporting them to the surface for processing. The scale of the proposed operations is enormous. Some license areas cover hundreds of thousands of square kilometres of seafloor. The environmental concerns are equally enormous. The abyssal plains where these nodules are found are among the most biologically sensitive environments on Earth. They may appear barren, flat expanses of mud and sediment stretching to the horizon, but they are home to communities of organisms that have adapted to conditions of extreme stability over millions of years. The nodules themselves, which form over periods of millions of years as minerals precipitate from the water around a seed object such as a shark tooth or a fragment of shell, serve as hard substrate for a variety of attached organisms, sponges, corals, foraminifera, and bacteria. Removing the nodules destroys not only the mineral deposit, but the biological community that depends on it. And because these communities grow and recover so slowly, the damage would be essentially permanent on any human timescale. The sediment plumes generated by mining operations are another concern. When machines disturb the seafloor, they kick up enormous clouds of fine sediment that can drift for hundreds of miles on deep ocean currents, smothering filter-feeding organisms and disrupting the food web over vast areas. Studies conducted in the Clarion-Clipperton Zone, a region of the Central Pacific that is the primary target for nodule mining, have shown that even small-scale experimental disturbances from the 1980s have left visible scars on the seafloor that have not recovered after more than 40 years. The organisms that were displaced have not returned. The sediment that was stirred has not fully settled. The deep ocean, it turns out, has a very long memory and a very slow capacity for healing. The debate over deep-sea mining is one of the defining environmental conflicts of our time, and it is far from resolved. Proponents argue that the metals in the deep ocean are essential for the transition to renewable energy, and that mining the seafloor is less destructive than mining on land. Opponents counter that we do not understand the deep ocean ecosystem well enough to predict the consequences of industrial-scale disturbance, and that destroying one of the last relatively pristine environments on Earth in the name of green technology is a contradiction that future generations will not forgive. The International Seabed Authority has been criticised by environmental groups and by some of its own members for moving too quickly toward issuing commercial licenses before adequate environmental safeguards are in place. As of now, no large-scale commercial mining of the deep sea floor has begun, but the clock is ticking, and the pressure to begin is growing. What is certain is that the deep ocean is changing, whether we explore it or not. Climate change is altering the temperature, chemistry, and circulation patterns of every ocean on Earth. The oceans have absorbed roughly 90% of the excess heat generated by human greenhouse gas emissions since the Industrial Revolution, and the consequences are being felt from the surface to the abyss. This absorption, while it has shielded the atmosphere from even greater warming, has come at an enormous cost to the marine environment. Deep water temperatures are rising, slowly but measurably, in basins that had remained stable for thousands of years. Oxygen levels in the deep ocean are declining, creating expanding dead zones where aerobic life cannot survive. The pH of seawater is dropping as the ocean absorbs carbon dioxide from the atmosphere, a process known as ocean acidification that threatens the ability of shell-building organisms, from microscopic foraminifera to enormous reef-building corals, to maintain their calcium carbonate structures. Some models suggest that by the end of this century, large portions of the deep ocean may become corrosive to the shells and skeletons of organisms that have relied on calcium for hundreds of millions of years. The thermohaline circulation, that great conveyor belt that regulates the climate of the northern hemisphere, shows signs of weakening. If it slows significantly or shuts down, the consequences for global weather patterns, agriculture and human civilization would be profound and unpredictable. The ocean that we are only now beginning to explore is also the ocean that we are simultaneously altering in ways that may prove irreversible. It is a paradox worthy of the deep itself. We are changing a world that we have not yet understood. We are destroying habitats before we have even discovered what lives in them, and we are doing so with a confidence that the ocean's history suggests is misplaced. The sea has been here for 4 billion years. It has survived asteroid impacts, ice ages, mass extinctions, and the rise and fall of countless species. It will, in all likelihood, outlast us. But the ocean of the future may be very different from the ocean of today, and the creatures that inhabit it may not be the ones we are only now beginning to name. The deep holds one more quality that is easy to overlook, and that is its capacity for silence, not the absence of sound, for as we have discussed, the ocean is full of sound, but a deeper kind of silence, the silence of time, the silence of patience, the silence of a world that does not need to be understood in order to exist. The ocean was here before there were eyes to see it, or minds to wonder about it. It filled its basins and carved its trenches, and hosted its strange luminous creatures in perfect indifference to whether anyone would ever know they were there. And in some sense that indifference is the most profound mystery of all. Not what the ocean contains, but the fact that it contains so much and asks nothing in return for the knowing of it. Beneath the Pacific Ocean, the largest body of water on Earth, the planet is restless. Along the margins of the Pacific Basin, from New Zealand north through the Mariana Islands, up to Japan, across to Alaska, and down the entire western coast of the Americas to the southern tip of Chile, the Earth's crust is cracking, folding and reforming itself in a continuous cycle of creation and destruction. This ring of seismic and volcanic activity, roughly 25,000 miles long and encompassing 75% of the world's active volcanoes, is known as the Ring of Fire, and while its most famous landmarks, Mount Fuji, Mount St. Helens, the volcanoes of Indonesia, are all on land, the vast majority of the Ring of Fire's activity takes place beneath the ocean, hidden from human eyes by miles of dark cold water. Submarine volcanoes are among the most powerful and least understood geological forces on the planet. They erupt with a frequency and violence that would be terrifying if they occurred on land, but because they happen on the ocean floor, they are usually invisible to the surface world. When a submarine volcano erupts at great depth, the immense pressure of the overlying water suppresses the explosive force of the eruption, containing the lava and gas in ways that are impossible on land. The result is often a slow, relentless outpouring of molten rock that builds up on the seafloor over time, creating seamounts, underwater mountains that can rise thousands of meters above the surrounding terrain without ever breaking the surface. There are estimated to be more than 100,000 seamounts on the ocean floor, and the vast majority have never been surveyed or even detected. But when submarine volcanoes erupt at shallower depths, the results can be dramatic and sometimes dangerous. In 2022, the eruption of the Hunga Tonga, Hunga Ha'apai submarine volcano in the Kingdom of Tonga produced one of the most powerful volcanic explosions recorded in modern history. The eruption column punched through the ocean surface and rose more than 30 miles into the atmosphere, reaching the mesosphere. The blast was heard thousands of miles away. Tsunami waves radiated outward across the Pacific and were detected as far away as the United States and Japan. Satellite imagery showed the eruption cloud spreading across the sky like an enormous grey flower, its shock wave visible as a ring of compressed air expanding outward at the speed of sound. The eruption injected an enormous quantity of water vapour into the stratosphere, an event that scientists believe may have contributed to temporary changes in global weather patterns in the month that followed. The Hunga Tonga eruption was a reminder that the ocean floor is not passive. It is alive, in a geological sense, and it can reach up and affect the surface world with terrifying speed and force. Submarine volcanic eruptions have been responsible for the creation and destruction of islands throughout human history. The island of Surtsey, off the coast of Iceland, was born from a submarine eruption in 1963, rising from the ocean over the course of 3.5 years as lava accumulated on the seafloor and eventually broke the surface. It remains one of the youngest islands on Earth and has been designated a nature reserve and a living laboratory for studying how life colonizes new land. At the other extreme, submarine eruptions have also destroyed islands. The legendary explosion of Krakatoa in 1883, while not strictly a submarine event, involved the collapse of an island volcano into the sea, producing tsunamis that killed more than 36,000 people across the Sunda Strait between Java and Sumatra. The caldera left behind eventually gave rise to a new volcanic island, Anak Krakatoa, which itself partially collapsed during an eruption in 2018, generating a tsunami that killed hundreds. The cycle of creation and destruction is endless, and the ocean is both the stage and the audience. The connection between the deep ocean and the surface world is one of the recurring themes of everything we have explored tonight. The trenches shape the currents, The currents shape the climate shapes the ice shapes the sound, and the sound, carried through thousands of miles of deep water, connects the most remote places on Earth in a web of vibration and resonance that we are only now learning to hear. The ocean is not a collection of isolated mysteries. It is a single interconnected system, vast beyond comprehension and old beyond imagining, and every part of it affects every other part in ways that science is still working to understand. Consider the journey of a single drop of water. It falls as rain on a mountain in Norway. It flows downhill into a river which carries it to the North Atlantic. There, chilled by Arctic winds and made heavy by the salt left behind when sea ice forms, it sinks thousands of meters to the ocean floor and begins a slow journey southward along the bottom of the Atlantic. It rounds the tip of Africa and enters the Southern Ocean, where it is drawn eastward by the Antarctic Circumpolar Current, the largest ocean current on Earth. It drifts through the deep Indian Ocean, eventually rising to the surface near the equator, warmed by tropical heat, and begins the long journey back toward the Atlantic as part of a surface current. The entire trip, from surface to abyss and back again, takes approximately 1,000 years. The drop of water that sinks today will not see the light again until the year 3000. And when it resurfaces, the world above it will be unrecognizably different. That is the timescale of the ocean, not days or years or even centuries, but millennia. The rhythms of the deep are so slow that human civilization, all of it, from the first cities of Mesopotamia to the present day, represents barely a single heartbeat in the life of the sea. We have been watching the ocean for a few thousand years. The ocean has been here for 4 billion. Whatever we discover, whatever we disturb, whatever we change, the ocean will absorb it, process it, and continue. It will be here long after the last human has drawn the last breath. And the creatures of the deep, those strange bioluminescent ghosts that drift through the darkness, will continue their ancient routines without any awareness that we were ever here at all. That thought might be unsettling, or it might be comforting. It depends on what you came here looking for tonight. We began this journey at the bottom of the Mariana Trench, in the deepest place on the surface of our planet, and from there we travelled outward and upward through layer after layer of mystery. We listened to the sound of an Antarctic glacier collapsing with enough force to shake the hydrophones of an entire ocean. We touched the smooth, glacially deposited stones of the Baltic Sea floor that had been mistaken for a spacecraft. We swam alongside the geometric sandstone terraces of Yonaguni, where nature and architecture meet in a place that refuses to declare which it is. We watched as giant squid, unseen by human eyes for centuries, finally revealed themselves to cameras in the darkness of the Pacific. We stood at the edge of the jacuzzi of despair and looked into a lake within an ocean, its poisonous waters preserving the bodies of everything that dared to enter. We counted the losses of 1968, 4 submarines from 4 nations, swallowed by the sea in a single terrible year. We measured the Bermuda Triangle against its reputation, and found the truth to be both more ordinary and more interesting than the myth. We descended to the hydrothermal vents, where life burns bright in the absence of everything we thought it needed. We drifted through phantom islands that existed only on maps, and we watched the largest migration on Earth unfold each night in the twilight zone, an invisible procession of trillions of creatures rising and falling through the water column, like a tide made of life. We learned that orcas are reshaping the hierarchy of the ocean's predators, that the midnight zone glows with a light that no human eye was meant to see, that the water filling the ocean may have fallen from space, carried on the backs of ancient comets, that the currents beneath the surface take 1,000 years to complete a single loop, that the floor of the ocean is being eyed by mining companies who see in its darkness a source of unimaginable wealth, and that for all our efforts, for all our technology, for all the centuries of exploration and study, we have mapped barely a quarter of what lies beneath the waves. The ocean does not give up its secrets easily. It never has. For as long as humans have sailed upon it, the sea has inspired both wonder and dread in equal measure. It provides and it takes. It connects and it separates. It is the source of life on this planet, and it is the final resting place of more human beings than any graveyard on land. It holds treasures and terrors in equal measure, and it holds them all with the same indifferent patience. If there is a single lesson from everything we have explored tonight, it is this: the ocean is not a mystery that will one day be solved. It is a mystery that deepens with every answer we find. Each discovery opens new questions. Each expedition returns with more unknowns than it set out to resolve. The more we learn about the deep, the more we realize how much remains beyond our reach, and perhaps that is as it should be. Perhaps the ocean's greatest gift is not the knowledge it yields, but the humility it demands. The reminder that there are still places on this planet where the darkness is deeper than our instruments can measure, where the pressure exceeds what our machines can withstand, and where the creatures that live there have never seen a human face and never will. Somewhere, right now, as you listen to this, a Siphonophore 150 feet long is drifting through the Pacific Midnight Zone, its body pulsing with blue light that no human has ever witnessed. Somewhere, a xenophyophore the size of a mango is sifting sediment at the bottom of the Mariana Trench, just as its ancestors did 100 million years ago. Somewhere, a hydrothermal vent is erupting in silence, its superheated plume rising through the darkness, feeding colonies of blind shrimp and giant tube worms that will never know the sun exists. And somewhere, on the vast unmapped plains of the abyssal seafloor, there are creatures living, feeding, reproducing, and dying that science has not yet imagined, let alone described. The ocean covers 70% of our world. We have explored less than a quarter of it. The rest is waiting in the same patient darkness that has cradled it, since before the first fish drew the first breath, since before the first continent drifted into its current position, since before life itself crawled from the shallows onto the shore. There is one more phenomenon of the deep ocean that deserves attention before we begin our ascent back to the surface. It is a phenomenon so counterintuitive, so visually surreal, that even seasoned oceanographers describe it with a note of disbelief in their voices. It is the underwater waterfall. Off the southwestern coast of Mauritius, in the Indian Ocean, satellite images reveal what appears to be a massive cascade of water plunging into the abyss just beyond the island's shoreline. The effect is striking. It looks exactly as though the ocean floor has opened up and the sea itself is draining into it, a waterfall beneath the waves. In reality, the illusion is created by sand and silt deposits being pulled off the shallow coastal shelf by powerful ocean currents and dragged down the steep underwater slope into far deeper water. The movement of the sediment creates patterns visible from space that mimic the appearance of a plunging waterfall. It is an optical illusion on a planetary scale, and it is beautiful. But the ocean does produce real underwater waterfalls, and they are far more impressive than any illusion. The Denmark Strait Cataract, located between Greenland and Iceland in the North Atlantic, is the largest known underwater waterfall on Earth. Cold, dense water from the Nordic seas flows southward along the seafloor and encounters a massive ridge in the Denmark Strait. As it spills over this ridge, it plunges more than 11,500 feet to the deeper ocean floor below. The volume of water cascading over this submarine cliff is estimated at roughly 175 million cubic feet per second, a flow rate more than 2,000 times greater than that of Niagara Falls. And yet, because it occurs entirely beneath the surface of the ocean, it is invisible to anyone standing on the deck of a ship overhead. There is no sound, no mist, no roar. Just an enormous column of cold, dense water falling silently through the dark. The Denmark Strait Cataract is not unique. Similar submarine waterfalls exist wherever ocean currents of differing densities encounter changes in seafloor topography. In the Southern Ocean, cold Antarctic bottom, water spills through gaps in the mid-ocean ridges and descends into the deep basins of the Atlantic, Pacific and Indian Oceans in slow, relentless cascades that redistribute heat, salt, and nutrients across the global ocean. These invisible waterfalls are among the most powerful hydrological features on Earth, yet they are so far removed from human experience that virtually no one outside of oceanography has ever heard of them. They are part of the ocean's hidden architecture, the plumbing of the planet, operating in silence at a scale that dwarfs anything built by human hands. The deep ocean is also reshaping our understanding of how life adapts to extreme conditions. For most of the history of biology, the assumption was that life required a fairly narrow range of physical conditions to survive: moderate temperature, moderate pressure, access to oxygen, access to light, or at least to food produced by organisms that had access to light. The deep sea has challenged every one of those assumptions, one by one, and in doing so has expanded the definition of what it means to be alive. Consider pressure. At the surface of the ocean, the pressure exerted by the atmosphere is roughly 14.7 pounds per square inch. At the bottom of the Mariana Trench, that number rises to approximately 16,000 pounds per square inch. For most terrestrial organisms, including humans, exposure to even a fraction of that pressure would be instantly fatal. Cell membranes would collapse, proteins would unfold, enzymes would cease to function. And yet, organisms at the bottom of the Mariana Trench operate under that pressure as comfortably as a bird operates in open air. Their cells have evolved membranes composed of different lipids that remain fluid under extreme compression. Their proteins fold into configurations that are stabilized, rather than disrupted, by high pressure. Their enzymes work not in spite of the crushing weight of 7 miles of water above them, but in concert with it. Researchers studying these organisms have discovered molecules and biochemical pathways that have no equivalent in surface life. Some of these molecules are of intense interest to the pharmaceutical industry, because the same properties that allow them to function under extreme pressure may have applications in medicine, particularly in the development of drugs that need to remain stable under harsh conditions. Consider temperature. Most surface organisms function within a range of perhaps 0 to 40 degrees Celsius. At the openings of hydrothermal vents, the temperature of the water can exceed 400 degrees. Just inches away from the vent, the ambient water temperature may be only 2 or 3 degrees above freezing. Organisms that live in this gradient have developed biochemistry that can tolerate temperature swings that would destroy any land-based creature. The Pompeii worm, Alvinella pompeiana, lives inside tubes attached to the walls of hydrothermal chimneys in the Pacific, its tail end exposed to water that may be as hot as 80 degrees Celsius, while its head end sits in water closer to 20 degrees. It is one of the most thermotolerant animals ever discovered, and the mechanisms by which it survives this gradient are still being studied. Consider food. In the surface ocean and on land, food chains are ultimately powered by photosynthesis, the conversion of sunlight into organic energy by plants and algae. In the deep ocean, sunlight does not exist. The only food that arrives from above is marine snow, the slow, continuous rain of dead plankton, fecal pellets and organic debris that drifts down from the surface. By the time it reaches the abyssal floor, much of this material has been consumed or decomposed during its long descent, and what remains is sparse and unpredictable. Organisms in the deep have adapted to this scarcity in remarkable ways. Some, like the sea cucumbers we encountered in the Mariana Trench, have become extraordinarily efficient at extracting nutrition from sediment, essentially eating mud and filtering out the microscopic organic particles it contains. Others have developed the ability to survive for extraordinarily long periods without food. The deep-sea spider crab can reportedly go more than a year between meals, slowing its metabolism to a crawl and waiting, motionless, for something edible to drift within reach. This capacity for patience is one of the defining characteristics of deep-sea life, a reflection of an environment where energy is precious and waste is fatal. And consider light, or rather, the total absence of it. Below roughly 1,000 meters, the ocean is in perpetual darkness. There is no sun, no moon, no stars, nothing but the blackness of water pressing in from every direction. The only light comes from the organisms themselves, those bioluminescent creatures that generate their own illumination through chemistry. For animals that live in this world, sight as we understand it is either useless or radically different. Some deep-sea fish have enormous eyes relative to their body size, eyes that can detect the faintest traces of bioluminescent light across distances that would be invisible to any surface animal. Others have abandoned vision entirely, evolving heightened sensitivity to vibration, pressure changes, and chemical signals in the water. The deep-sea environment has produced sensory systems that we are still struggling to comprehend, ways of perceiving the world that have no parallel in human experience. All of these adaptations to pressure, to temperature, to scarcity, to darkness represent billions of years of evolutionary refinement. The deep ocean is not a hostile environment that life endures in spite of itself. It is an ancient and stable habitat in which life has had more time to adapt than in almost any other environment on Earth. The conditions at the bottom of the ocean have remained remarkably constant for tens of millions of years, changing far more slowly than conditions on the volatile, weather-beaten surface. In this stability, evolution has had the luxury of time, producing solutions to the challenges of deep living that are elegant, efficient, and profoundly alien to surface dwellers. We look at the creatures of the deep and see strangeness, but from their perspective, the strange ones are us, fragile beings who can survive only in a thin sliver of atmosphere, clinging to the sunlit skin of a world that is overwhelmingly dark, cold, and deep. If you have made it this far, you already know that the deep sea is not a place of simple answers. It is a place of questions that multiply in the dark, of mysteries that outlast the people who first stumbled upon them. Some of the stories we shared tonight will be resolved in the years ahead. New technology, new expeditions, and new minds will illuminate corners of the ocean that are dark today. Others may never be answered. The ocean is under no obligation to explain itself. Thank you for spending these hours with us in the deep. If you enjoyed this journey, consider subscribing. We release new explorations of the unknown every single week. And if a particular mystery stayed with you tonight, tell us about it in the comments. We read every one, and we are always looking for the next story the ocean wants to tell. For now, rest easy. The deep will still be there in the morning. It has been there for 4 billion years. It will be there for 4 billion more. And somewhere in its darkness right now, something is moving. Something is glowing, something is alive, that has never been seen by any eye but its own. That is not a reason to be afraid. That is a reason to keep looking. The ocean remembers what we have forgotten. It holds the bones of ships that sailed before any living nation existed. It holds creatures whose ancestors watched the dinosaurs come and go. It holds water that fell as rain before the pyramids were built. Water that sank to the bottom and has been circling the planet in slow, dark silence ever since. We are newcomers here, brief, curious visitors on a planet that is, first and always, a world of water, and the water is patient. It does not hurry. It does not demand. It simply waits in the cold and the dark and the quiet for whoever is brave enough or curious enough to come and listen to what it has to say. Good night.